Moving on to section 11C, where we will talk about acceleration, whereas last time we talked about velocity. And there you see a very quick definition of acceleration, changing motion. There's a tiny bit more to that, and we're about to see. Are we ready to begin? Notes 11C. Acceleration is any change in velocity. And remember that velocity includes both speed and direction. And that happens over a time interval. It takes time to go from one speed to another. So we'll consider the time interval also when we do our calculation. And yes, I said calculation. Now first, let's consider something else. Okay. Notice the definition again. Any change in velocity, which also means any change in speed or direction. So if I'm going around a curve, but maintaining my 10 miles per hour all the way, did I accelerate even though I kept the speed the same? The answer is yes, because what changed? The direction changed. Acceleration is any change in velocity, and since velocity also includes direction, any change in direction is also considered acceleration. Here's the formula. Acceleration equals a change in velocity over time. Write that more like you're used to, up and down. Therefore, acceleration is, to figure out the change in velocity, we will subtract final minus initial, very much like we did with displacement in our last session, and then divide by time. And now we're about to see examples using this formula right here. Ready? Let's do it. We're in the school zone. We have to slow down because of the kids in the school zone, and we're going 5 meters per second, which is about 11 miles per hour. When we get out of the school zone, we can then get up to the normal speed limit of the road. 20 meters per second is just about 44 to 45 miles per hour, just to give you an idea of what the speeds are and what you're used to. And we take 5 seconds to go from 5 to 20 meters per second. All right, let's fill this in. We're going to calculate the acceleration. Remember the formula. Get that color we can see better. Vf minus Vi over t. The final velocity is what we got up to, 20 minus the initial velocity of 5 in meters per second. And we divide by the 5 seconds. All right, now just do the math. This is 15 meters per second divided by 5 meters, or 5 seconds. I'll correct that. I make mistakes. Now look at the unit here. Obviously 15 over 5 is 3, but look at the unit. Meters per second per second. We're dividing twice by seconds. So it's meters per second one time, then we're dividing by seconds again. When that's the case, if we're dividing by the same unit twice, we can write it this way, and it looks like even we are dividing by seconds twice. So there's where we get the unit meters per second squared. We'll get a lot of chances to practice that. So here it is typed more neatly. Acceleration is Vf minus Vi over t. Fill in your numbers. Since they're both meters per second velocity, we can write the 20 minus 15 in parentheses and simply put the unit to the outside. Then we divide by the time. We'll have many practice problems here. And just do the math. 15 meters per second divided by 5 seconds. Again, we're dividing by seconds twice, and that's why we end up with meters per second squared. It even looks like it says meters divided by seconds twice. The unit is meters per second squared. What this means is that we are increasing our speed 3 meters per second for every second of time that we take to accelerate. So starting off at 5, after 1 second, we're now at add 3, that's 8. After 2 seconds, 11. 3 seconds, 14. 4 seconds, 17. And 5 seconds, we've hit 20 meters per second. We're increasing our speed 3 meters per second of time for every second, or 3 meters per second of speed for every second of time. Ready? Okay. What if we slow down? What if we're going 20 and we have to slow down to get to 5? Well, deceleration you've probably heard of. That does mean we're slowing down. Okay, in this case, we're driving 45 meters per second, which is flying on the highway. We are booking it. Remember, if 20 meters per second is around 45 miles per hour, okay, that's more than double. We're going in the mid-90s miles per hour here. Uh-oh, we see the officer. We're going to slow down to 25 meters per second, which is more like highway speed. But it takes us 10 seconds to do that because we want to slow down gradually and safely. Okay, let's do the math here. Same formula whether we're getting faster or slower. Vf minus Vi over t. This time we are decelerating. So Vf is going to be the larger number. This is going to be our 45 minus 25. Oh, you know what? I got that backwards. 25 minus 45 meters per second. Hey, see a mistake? Correct the mistake. And we're going to do it in 10 seconds. Now, thing is, since I'm slowing down, I want my answer to be negative. That means I need small minus large. 25 minus 45 is negative 20. That's meters per second divided by 10 seconds. Well, negative 20 over 10 is negative 2. And remember, meters divided by seconds twice. So negative 2 meters per second squared. We have to get a negative number here because that means our speed is slowing down, getting lower. So deceleration, there's your formula. A equals Vf minus Vi over t. Fill in the numbers, 25 minus 45. Vf is 25. And then this happens over a 10-second time interval. So negative 20 comes from the 25 minus 45. Then we're dividing by 10. That's negative 2 meters per second, or meters divided by seconds twice, so meters per second squared. And that's how we calculate negative acceleration or deceleration. Exactly the same formula. So how do you know if you should have large minus small or small minus large? If your speed is getting higher, you need to end up with positive. That's large minus small. If your speed is getting lower, that means you're decelerating. You have to end up negative. That's small minus large. Ready? Free fall. Now I made these fall because we're talking about free fall. Objects always fall with the same gravitational pull. Many people think heavier objects automatically fall faster. Well, in many cases that realistically happens. Scientifically speaking, there are reasons for that. Heavier objects are typically denser, which means those objects will cut through the air resistance better. There's always a force pushing things up. Mass and inertia, which means a resistance to a change in motion, are going to balance each other out. You're going to get the same net pull. So gravity pulls on every object exactly the same. It's just that objects that meet more air resistance will fall more slowly. So take a piece of paper, a regular sheet of notebook paper, hold that flat and let that drop. You'll notice that the paper sways and falls slowly to the floor. Take that exact same paper with the exact same mass and ball that up as tightly as you can and drop that balled up paper from exactly the same height. That balled up paper will drop straight and much faster because there's much less air resistance pushing back up. Gravity pulls on both papers exactly the same, but the balled up paper has less air resistance, so that falls faster. It's not always weight and mass, it's air resistance. All of those combined will determine how fast an object falls. But disregarding air resistance, and in introductory levels, we have to disregard some things that really do happen. Disregarding air resistance, every object would fall the same. Ready? Can we figure out how tall something is simply by allowing an object to fall? That answer is yes. The acceleration is due to gravity. At this rate right here, Gravity pulls on every object with an acceleration rate of 9.81 meters per second squared. So an object falling, disregarding air resistance, will gain 9.81 meters per second of speed for every second of time that the object falls. And since acceleration is a vector, we need to include the direction. And gravity always pulls things down. So this is a number you're going to memorize and you're going to use all the time. The acceleration of gravity on Earth is 9.81 meters per second squared down always. Acceleration is a vector. Now, can we calculate the distance that an object falls? Yes, we can. Let's say we want to know how tall the bleachers are. We can simply take an object to the top of the bleachers, drop that object, time how fast will the object hit the ground, and then do this calculation right here. Falling distance is 1/2 times gravity, 9.81, times the square of the time that it takes. We're going to do an example right now. Ready? Okay, here is the example. A stone falls from a cliff and hits the ground 5 seconds later. How high is the cliff? Now, something that is actually coming right at the end of the notes. If we kick, here's the cliff. If we kick the object straight forward, the object will actually fall kind of like this. Or if we drop the object straight down, assuming this is perfectly straight out, whichever way we kicked these, that object would hit the ground at the same time, even though this would be further out. And that's coming up a little more later in the notes here. Okay. Now let's fill this in. I'll tell you what these lines mean in just a moment. Here's your equation. The falling distance, how high the cliff is 1/2 gravity times the square of time. So notice what I did with the colors. Again, many practice problems are coming. Fill in G at 9.81 meters per second squared. Fill in T at 5 seconds. Now, because T in the formula has the little bitty 2, the little bitty 2 goes outside the parentheses when we fill in time. That means the 2 goes on both the 5 and the seconds. This is inside because this is not on the number. This little bitty 2 is part of the unit. We will not square 9.81. Okay, seconds squared will cancel with these seconds twice. So those are going to cancel. And look, only meters is left, which is the unit for distance. Now, before we actually calculate, let's estimate. This number is very close to 10. 5 squared is 25. 25 times 10, that's 250. Half of 250 is 125. This means our answer needs to be pretty close to 125. Now, let's do the exact math. 5 squared is 25. 1/2 times 9.81 times 25, that is 122.63, which is pretty close to 125 that we estimated. I say estimate first before doing the actual calculations so we know whether or not we got the answer correct. I needed to be very close to 125, and I am. And since 9.81 is just a tiny bit under 10, then my answer needs to be a tiny bit under 125. So I can tell right here I did the work correctly. The unit for distance in physics is either meters or kilometers. Meters for smaller distances, kilometers for much larger ones. This is going to be meters. Besides, the unit for gravity is used in meters, meters per second squared. So I need that kind of matching unit in my answer. Ready? Now, two-dimensional motion. Look at the circle right here. Okay? Assuming that we keep the same speed going around this circle. That's like you may be having, this is going to look funny, but you get a ball tied to a string and swing that above your head over and over and over again at the same speed. If we let that ball go, that ball's going to fly off in a straight line, and then gravity will pull the ball down. Remember, changing direction is acceleration because we've changed direction. And change in direction means we've changed the velocity, even if the speed stays the same. Now, I tried to match the colors with the words to the picture here. In the bluish color here, we have what's called centripetal acceleration. This is movement in a circular path, as you see in the blue right here. The object continues to go around and around in this circular path. And you now notice this green arrow here. There's a force that's pulling the object toward the center of that circle. Think of the planets, the sun pulling on the planets to keep those planets in an almost circular pattern. And we've talked about atoms before, the electrostatic force of the nucleus and the electrons, keeping the electrons in a circular pattern revolving around the nucleus. Well, if you were to tie that ball to a string and swing that above your head in a circular pattern, like I showed you a moment ago, the force, the tension of the string would be pulling that ball toward the center. The moment we let that string go, that ball flies off in a straight line, at least horizontally speaking, but then of course being pulled to the ground by gravity. That centripetal force, the force that pulls the object back toward the center. Centripetal acceleration is the object actually making the circular shape. Example, go around a curve in a car. If you take a sharp curve at a slow speed, that curve is easier to get the car around because we don't have a strong force pulling back to the circle. I need to pause for just a moment here. And then, if we were to take that curve at a much faster speed, well then it would be harder to control the car for a couple of reasons. The car wants to keep going in the straight line, and it's harder to pull that car around the curve. Then we have a centripetal force right here, pulling the object in toward the center, but the inertia of the car wants to keep the car moving in a straight line. So these two are battling each other. That's why when we go around a sharp curve, we need to slow down because it's very dangerous with all the forces pulling on the car, especially if there's a wall like I-95 through downtown Jacksonville. So be very careful. Go around a curve, slow down, and that's why you'll see the speed limit signs reduce the speed that you're allowed to drive, and then the yellow signs will tell you slow down to 30 or 25 around a sharp curve coming ahead. And that's all because of centripetal acceleration and centripetal force. Ready? All right, almost done. I mentioned this just a moment ago. Okay. See the cannon right here. The cannon is set to shoot the cannonball perfectly horizontal. Now we know that gravity is going to pull that cannonball down instead of complete that straight line here. But let's say, and there are actually small little toy cannons that can do this. I don't have one though. You get a cannon that'll shoot the ball horizontally and at the same time drop another ball perfectly straight down. Which one would hit the ground at the first? They would actually both hit the ground at the same time, disregarding air resistance. You already know that gravity will instantly start to pull the object down. So the horizontal motion is also being affected by the vertical motion of gravity, or actually I should say the vertical force of gravity. So you see here, these are the time intervals for the horizontal component of the motion. And the cannonball heads to the ground. Now, if we were able to drop another cannonball at the exact same time, perfectly straight down, well, I want you to notice here, the height of the cannonballs, assuming I drew this correctly, are going to be the same after the same time interval. And that's because gravity doesn't care about horizontal motion. Gravity pulls every object down exactly the same. So the cannonball going straight down would maintain the same height as a cannonball starting off horizontally, but actually ending up in this curved path right here. Here's somebody who hit the baseball maybe for a home run, and the ball follows this path. Of course, I can't draw well. And assuming no wind pushing the ball back, we have kind of the same curve on both sides, one half going up, the other half going down. Well, that's because in what we call projectile motion, horizontal and vertical motion are completely independent of each other. We don't care, or they don't care about each other. Okay, what you can do to verify this, if you're able to walk fast with the ball in your hand, and while you're walking, throw the ball perfectly straight up, that ball should come back down in your hand even though you have taken a few steps. And it takes practice to be able to do that because you want that ball to go perfectly straight up. So if you were to start here and throw that ball up, by the time you're here, you'd be catching that ball. So if you're here and throw that ball straight up, that ball's already moving horizontally and will come down and you'll catch it right there. It takes practice to do that. But that's because horizontal and vertical motion are completely independent of each other. Okay? If you were to throw a ball perfectly straight forward, the force, just like this cannonball here, will shoot the ball perfectly horizontal to the ground, but then gravity is going to pull the ball down. And if we put these two components together, we get this motion right here. Now, some of you maybe already be in geometry class, and the rest of you are in Algebra 1, so you may not have seen this a whole lot yet, but you will very soon in the year. Something called a parabola. The motion is a parabola. The trajectory is called parabolic, but this curve is called a parabola if this was a perfectly smooth curve. This one is. And that's the motion of what we call a projectile motion. A projectile is something that is thrown up or horizontally, but not perfectly straight up, but with some horizontal motion, and gravity is going to pull that object down as the object continues to travel horizontally. And disregarding resistance, we end up with a perfectly parabolic shape. Ready? And that ends Notes 11C about acceleration. All right, look forward to doing the practice problems with you. Good night.